Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Very loud. We can sort that out. Okay, is that good? I think it is. All right. Okay, so what we're going to do today is we're going to go through as many, or a few at least, of time series examples. So this is sort of to get you a little bit prepared for the assignment. So I just wanted to point out one thing I've put up online is a bit of a summary of what we talked about towards the end of, I know that's a lot of text, but anyway, what we talked about at the end of the last lecture, which is sort of the set of steps that you want to go through for analysing time series. So I sat down and I wrote them all down in a bit more detail after we spoke about them at the lecture. Okay, so you can see they're all there. Turn it into a time series, plot the data, transform, trend, seasonal, etc., etc., etc. So that's, I just put that up on Wattle, so I'll show you where that is. It's with the assignment, it's right under the assignment itself, okay? So if you didn't get those steps at the last lecture or you wanted to read through them again, there they are right there. So hopefully that'll help people with the steps. Okay, so what we're going to do is we're going to start by looking at the kiwi fruit data, and then we're going to move on and look at some of the tutorial data. Again, because I know for most people this is the first time you all have done time series, so good to spend some time looking at some examples, I think. We have some time. So, all right, so the kiwi fruit data, this is monthly data on kiwi fruit exports from New Zealand. It starts in July 1981 and goes on for several years. So first thing we want to do is we take the original data and we make sure that it's a time series with the right frequency. So inside the mass library there's a TS function which turns things into time series. We give it the vector that contains the data. Then the next two bits tell us how often it's measured per year. So frequency is 12, means it's measured 12 times a year. And we tell it when it started. So start is in 1981, month 7, which is July. Okay, so first thing we do when we deal with a time series is we set up the time structure. Okay, and so again, thinking forward to the assignment, a little bit different. The data is, it's the coal data. So a few people have been asking me, what sort of data is it? It's data of US coal production. Okay, so it is US. Frequency is 1, right? It's measured annually. Okay, and therefore you don't have to worry too much about the start. It's already set up in the data set there with the right start year. All right. So the data set that you've got, it's called bicoal.tons, just in case you haven't started yet or haven't looked at it yet. You'll see if I just type that, it tells me it's a time series, start in 1920, frequency is 1. So it's already been set up as a time series. All right, so we're going to start by looking at the kiwi fruit data. We started this process last week, and we're going to go through our steps. So what I want to do today is when I go through all the different examples is go through the steps, reflect on the steps, okay? So the first thing you ever do is you plot the data, you look at this and you ask yourself some basic questions, and the questions are, is it homoscedastic? That's the first thing. Does it have constant variance? In other words, is the width of the data sort of fixed as you move across? Here, clearly not. It's narrowed down this end, blown out down the other end. So this has a very much heteroscedastic structure, right? It's going from low variance to high variance. So we're going to want to do something about that. The other questions you ask yourself, is it trending? Well, yeah, it seems to be going up. Okay, at the moment it looks like it's going up non-linearly, but we're going to transform it, so we'll recheck that. And there is this seasonal component, right? Every year, I guess when kiwi fruit is in growing season, it goes up. When it's not growing, it hits bottom, okay, and so on. All right? If you actually look at the data carefully, you'll see when it hits the bottom, the lowest value is 1, okay, not 0. And I think that's been modified, because probably it's 0, right? But one of the things you want to do is you want to take transformations of it. So I think the transformation that you end up with is log. Log of 0 is undefined. So the data's been messed with, so you can take a log. Okay, it's a sure sign. Because you know 1's not right. You know that's been made up. And so it's to allow that transformation to occur. Okay? All right, so let's keep going. Let's have a look at a plot of the log data. And you can try different things. You can try square root. I mean, I'll show you that. So there's the log data. If you put square root in instead of log, easy to do, you'll see still heteroscedastic, right? Still growing a little bit in terms of spread. So, I didn't know at the start this was going to be log. You try a few things and you end up at log, okay? And that kind of makes sense in terms of empiricism. I don't have any sort of physical model that suggests export should be on the log scale, right? But we end up on the log scale. So you can try different transformations there. Generally speaking, once you've tried square root and log, you're probably pretty much tapped in terms of sensible transformations, but anyway. All right, and there's the low S curve that runs through the log data. And you can see that looks pretty much like a straight line. Not quite, but, would I fit a cubic to that? Probably not, because it doesn't look like it bends that much. So I'd probably be inclined to look at that and go and suggest that it's linear, okay? And in fact, if you go ahead and put a straight line on that plot, you can see it does seem to fit the data pretty well. All right? So I would suggest for this data, the trend on the log scale, the trend is probably linear. Now, you can fit whatever you want, right? So again, I get a lot of questions around, well, what if I fit a cubic and it's wrong? Well, the answer always is, well, it's not wrong. It just might not be as good as you could do, okay? If you fit a cubic to this, I think you'd be overfitting it. Yes, you'd capture those little curves, but at what cost? 2 extra parameters, is that worth it? Probably not. Again, once you fit the model, you can always check and see whether the coefficients of the cubic term and the quadratic term are significant. They're probably not, in which case you'd dump them. But again, you've got to trust your eyes on these things, and so I see a straight line, and I think a straight line's probably enough. So we go ahead and do that, and we'll fit that line. There we go. And create the fitted values. All right, so the trend is probably linear. Once you fit the trend, you then want to create the detrended data. So the detrended data is what you get if you use the residuals from the model that you've just fit. So we can do that a couple of ways. We can either take the data and subtract off the fitted values, those are the residuals, or you could use the residuals function, okay? And this is the detrended series. So all this has done is you've logged the data, you've fit a linear trend, and then you've subtracted off that trend so that this thing's now flat, and you can see there's still a lot of structure left, right? You can still see that wiggliness, those are the seasons, and there's error as well. You'll notice one thing, which we'll talk about a little bit, not a whole lot. You'll notice that there does seem to be something going on at the bottom here. This isn't flat along the bottom. It looks like it's got a little trend to it. So we'll talk about how you might handle that, and we'll talk about good models, better models, and so on, of how you might deal with that. Because the data is measured 12 times a year, you've got frequency 12, you can actually run STL on it. So let's do that. So here I've got STL of log kiwi, s.window equals periodic, says fit a seasonal, and t.window is 99. This is because I've got, how many data points do I have? Let's find out. Length of kiwi. I've got 108 data points. Oh, that's a big window. I probably could use a t.window of about 60. but I've gone a little bit higher. Doesn't really matter. And I'm going to plot the result of that STL output, and we get this. So okay, so this is your STL output. Again, it's just to more or less confirm what we've seen. The third panel here is your trend. So I fit a straight line. This looks a little bit curved, so some people might say quadratic. Okay, so again, neither is right, neither is wrong. I think because the curvature in this is so mild, I'd be inclined not to go quadratic. The other thing I want to point out about these STL outputs is, see these guys on the right, these little markers here? These reflect the relative size of each of the windows. So the way to interpret that is that, because the 4 panels have the same width, right? It puts 4 same width panels on the page. So this distance from here to here on this plot is the same as this distance on the third plot, okay? So what that tells you is that that trend, even though it looks pretty steep, it ain't steep at all, right? Because it's been scaled so that it fits in this panel. So this width here on this plot is the same as this width there on that plot, and so on, okay? So it's not as steep as it looks. Is that an effective graphical display? Probably not. What would be better, this is just the way STL was written, what would be better would be to create a function which creates 4 panels all on the same scale, right? So from the point of view of graphical construction, you could write your own STL function and do that if you wanted to. But anyway, we're sticking with what's in R. So there's my original series, there's my seasonal, there's my trend, there's my irregular. Okay, put a title on. Here's the month plot. So you can see here's January, February, March, April, May, June, July, August, September, October, November, December. So what do you notice? You notice, well, January, February, March, April, they're all different. Then you've got this extended period where you've got, essentially, you could probably throw a single flat line over all of these, okay? So what's going on there? Well, that'll be the non-growing season, right? That'll be the non-growing season. That's when things aren't happening. And so, which is winter in the southern hemisphere, basically. Kiwi fruit aren't growing. And so you could fit a single flat constant across, what would it be, May, June, July, August, September, October, right? That 6-month period, okay? Then you've got November, December, and December has started to come down here. So when we fit our seasonal effect, there's a few different ways you could do it. The simplest way you could do it is to say, look, every month is different. I'm going to fit a factor which has a separate constant for each month, okay? So to do that, you'd go, V is factor, it starts in the 7th month, so you've got 7, 8, 9, 10, 11, 12, that's the first year, the end of the first year. Then you've got 8 full years of data, so 8 replications of January, February, March, April, right through December. So 1 through 12 repeated 8 times, and then it finishes 1, 2, 3, 4, 5, 6. It finishes with the first half of that 13th year. All right? So you set up your seasonal factor like that, okay? And then you can actually fit it. So we'll just go down here and fit it. A little bit lower, so... Oh, that's a bit more complex. So let's go ahead and fit it. So we go and look at our... So this is model 1. Where are we? So we've got RLM log kiwi tilde time kiwi, so that's your linear term, plus V. That's your seasonal term. Not, didn't mean to do that. Where is it? Plus V. I'm not putting a line on a plot, I'm just fitting them all. So this is model 1. This is a really simple model. It basically says, I've got a linear trend and I've got a separate constant for each month. So let's have a look at that model. Okay, so you've got an intercept of minus 635. Remember, this is data on the log scale, so having a negative intercept doesn't matter, right? This is the coefficient of time, so this is the amount by which the log rises every year. Okay, then this is February, March, right? You know what happened to January? January's sucked into here, right? January's your baseline. So January's the baseline, and you get February, March, April, May, June, July, August, September, October, November, December. All right? So that would be like a full model that's got a constant trend, a linear trend, and a constant seasonal, where the seasonal is a separate constant for each month. All right? Now, what I wanted you to notice about this is we looked at that plot and we said, well, you know, there's February, there's March, there's April, then May, June, July, August, September, October. Look at these numbers. 4 point something, 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 4 point something. Okay, they're all pretty close to one another. So one alternative model that you could fit would be to fit a single constant over this 6-month period. Okay? So I'll show you how to do that. And then November, December. Alternatively, you could go, okay, well, these numbers, this one, this one, this one, this one, and this one are pretty much the same, but I might fit a different one for this one. It's a bit different. So you can do different things. You've got a lot of flexibility in modelling, right? And again, this is, you know, both a boon and a curse. So many people say to me, you know, this is the model I fit, am I right? And the answer is always no, right? No, you're not right. You might be close, you might be good, you might be great, but it's not right, okay? So you can fit a lot of different models. So I'm going to show you how to fit the one that has a different constant for February, March, April, and then has a single constant for May, June, July, August, September, October, okay? And then separate things for November and December. So let's do that, okay? So this is how you might do that. So I'm going to set up a new factor, okay? So I'm going to set up, that's not quite right. Okay, so I'm going to go V, do it properly. You can see I fit a different model in the notes. That's okay. V is factor. Okay, what do I do? So the thing starts in July, right? July's the seventh month. So that's this one here. Okay, data starts in July. So this is season 2, 3, 4, 5. Okay, 2, 3, 4, sorry. 2, 3, 4. This is season 5. Okay. If I think this season has the same constant, this is going to be still season 5. 5. This is still season 5. 5, 5. I could probably put a 5 here. Okay. Then 6, 7. All right? So now my factor, instead of looking like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 months, looks like 1, 2, 3, 4, 5, 5, 5, 5, 5, 5, 6, 7. Okay? So let's do that. So July is 5. Okay? What's after July? August, 5. September, 5. October, 5. November, 6. December, 7. So that's the first bit of the data. Then I go repeat, C, so January, February, March, April, May, June. June is 5. July is 5. Right? August is 5. September is 5. October is 5. November is 6. December is 7. Get it? I'm going to do that 8 times because that's 8 full years of data. And then I finish the year with January through June. 1, 2, 3, 4, 5, 5. All right, so it's pretty complicated. Oh, man. Error. error. Just because I have a space there. No, that's better. That's better. Okay, so let's run through that again. Because I know it's a bit complicated. All right. Data set starts in July. We've decided that's season 5, right? And then season 5 goes on for a while. July, 5. August, 5. September, 5. Right? October, 5. November, 6. December, 7. Right? That's the first 6 months of the data. Then you have you have 8 full years. What's a year? January 1, February 2, March 3, April 4, May 5, June 5, right? July 5, August 5, September 5, October 5, November 6, December 7. Okay? So I'm putting I've got a bunch of 5s in the middle there because I'm regarding that set of months all as having the same constant. Right? That's why I'm giving them the same month. Okay? And then when I finish the data, I've got January through June. 1, 2, 3, 4, 5, 5. Right? So it's complicated. Okay, why am I doing it? Who knows why I'm doing it? Not to make your lives hard. Who knows why I'm doing it? Lauren. Yeah. So what's the benefit of doing it? Statistically. Close, saves, fitting parameters. Yep. So see, if I fit a separate thing for every month, I got to burn 12 parameters, right? One for each month. But if I know that for 6 of those months I'm getting the same number, I can force that, and by forcing it, I'm going to save myself fitting 6 parameters. I'll fit 1 instead. Okay? So I'm going to get a smaller model. And remember, in statistics, small is good for models, right? So that's the goal of doing this. Now, we're going to have 2 models in front of us, right? One is going to be a separate constant for each month, and the other is going to be this sort of weird model that's got a separate constant for 5 or 6 months, and then a different constant for a block of 6 months. These are 2 alternative models, right? Which one's right? Neither. Which one's better? Don't know yet. Okay? You fit both and you check it out. And this is how modelling works. So, yeah. Anyway, you had a question.
How do you know this data began from January? I mean, I think this data began from
July. Yeah.
So how do you even fit the model from beginning to July? This should be the first one is July is the baseline, and others is the baseline.
Yeah, you reflect that through the way you set up your seasonal factor. So your seasonal factor starts with a 5, which is the July month, and that's how you do it. So you basically set up your season so that the numbers in that seasonal vector line up with when your data starts and ends. Okay? So if your data started in January, that seasonal vector would start with a 1. 1, 2, 3, 4, and then, yeah. Okay? So I know this is a little bit complicated, but I just wanted to show you an alternative here for these different approaches. Okay, so let's go ahead now. So there's my new factor. Okay, so now I can go ahead and fit the model. I'll call it model 2. Model 2. If I look at model 2, much smaller, right? Instead of having 12 things, I've got 7. Okay. Intercept, coefficient of time, so this is my linear term, February, March, April, May through October, right? So all of these are the same now, forced to be the same, 4.66, November, December. Okay? So it's a much smaller model, probably pretty similar explanatory power. So if you wanted to compare those models, you could actually have a look at the R squared for each of them and see how you are. Okay? So if I do a summary of model 1, I get this. Okay? So you can see everything's significant. All right? To do an R squared, I need to use ln. So let's go back and fit it with ln. So model 1. So here's model 1 again, refit. Using ln. and I'll refit model 2 using LM. Oh, people often ask me, what LM, RLM, which one do you use? Truthfully, for time series, it's not going to matter because there aren't any outliers here. So you might as well have just used LM. I get so used to using RLM that I just do it by rote. So let's refit those using LM. Okay, now let's have a look at summary, model 1. Okay, so the model 1 summary gives me an adjusted R squared of 88%. 88%, right? How about model 2? Model 2. %, right? So I've saved 6 parameters, or sorry, 5 parameters, and I've got the same adjusted R squared, okay? So that's almost a sure sign that you want the smaller model. You're not doing any better by adding all those extra parameters. And it's because, look at the picture, right? So different, same, different, right? So where you see same, you might as well fit same and just use a single constant, okay? Again, neither model's right. I think the model that has the same constant across that period is better because it's smaller. Okay, that's it. That's it. So we're going to go with model 2. Okay, so let's say res equals residuals from model 2. Okay, and now let's do a Box-Jenkins identification and see where we're at. So there's your ACF at the top, there's your PACF. Now something weird happens here, something a little weird happens. You can see the ACF starts with a big spike of size 1, right? That's your lag 0, so it has to be 1. Then all the other spikes go in within those dotted lines and stay there, okay? So I think the series is stationary, so that's thing 1. Now you look at your PACF and you ask, which is the last spike outside the dotted lines? Okay, well that's inside. This one here, it just touches the dotted line. Is it inside or outside? Well, if it's inside, I'm good. If it's outside, I'm sad because I've got to fit an AR12. You're kidding me? AR12? I'm not going to fit an AR12, right? And now it looks like white noise, right? Because even the first spike is inside, okay? So you've got choices now. You can either fit an AR12, in which case you've probably got a model that's overfit to hell, okay? Or you can say, well, I think I've got all the structure now, white noise. I don't know that the data is white noise. If I do a plot of the residuals, let me do this on a full screen. Plot 12108 against residuals. Type equals L. There's my residual plot. And you can see it doesn't look independent, right? It doesn't look independent. It's wiggling around. It's got that sort of mountain structure again. By the way, the spikes, people say that still looks like it has a period in it. If you count from peak to peak, you see the numbers aren't quite regular. So it's not a regular thing. So it's an irregular series. To me, that looks more like an AR1 than it does like white noise, but it's close, right? It's close. It wiggles around a lot, but I'd expect white noise to wiggle around more. So you could probably fit an AR1 to this, okay? So your Box-Jenkins identification kind of says, there's not much left. But I look at that first plot and I make a judgment that I think there is some dependence there. And this one's getting close to the dotted line, so I'd probably fit an AR1. So how would I fit an AR1? I'd go fit AR equals rake of res. Okay, goes ahead and it does it. Fit AR dollars coef first column. So the coefficient for my AR1 would be 0.133. Quite a small number. Quite a small number. And I could look at the residuals from that to then see whether there's any structure left. Okay, so that's, and then we look at residual plots, okay, to make sure that everything's hunky-dory. Okay, so where have we got to? So one of the things I wanted to point out when talking about this data set is that the enormous number of choices you get when you make an analysis, right? So right at the get-go, you have to choose the transformation. Well, here log kind of seemed right, but you'll run into series where square root log, it's hard to choose. You just have to choose one, right? The one thing you can't be is afraid of making choices. If you're afraid of making choices, you ain't going to be a good data analyst, right? Because data analysis is choice after choice after choice. And everyone leads you down a path that will not be correct, but it might not be wrong either, okay? So when you're a data analyst, you're just living in the world where nothing's right, nothing's wrong. Well, there are wrong things, but you know, there's a lot of right things, and you're just trying to get the best model you can get, right? So you had to choose the transformation. You had to decide whether it was a linear trend or not, okay? Well, some people might fit a quadratic, okay? Then you had to look at the seasonal. You saw there were choices there. You could fit a separate term for every month, or you could go ahead and recognise that for 6 months of the year it's pretty flat, fit a separate term for that 6 months, and so on, right? Then when it came to modelling the dependence, you've got lots of different pieces of evidence. You've got your Box-Jenkins identification, which kind of says you've captured all the dependence. Then you've got the picture of the residuals, the time series plot of the residuals, which says it still looks a bit dependent. So you can choose between white noise and an AR1. And you end up with a model, okay? And your model might look different to everyone else's model, and that's okay. The guiding principles are, choose the smallest model you think you can, right? Because smaller is better, provided you don't lose too much explanatory power. And trust your eyes, right? I mean, the whole point of having a whole course on graphical data analysis is to look at graphs and to make decisions based on those graphs, okay? And that's where we end up. All right, I want to look at a different data set. So I'm going to look at the tutorial. I'm going to start with tutorial 8 instead of tutorial 7. I'll tell you why. I'm actually going to look at the second data set here. And the reason I'm going to do that is because it's probably the one that's most like the assignment data. All right? So, looking at this, the annual report of the Australian Tobacco Board contains data on the annual duty paid clearances of Australian cigarettes and tobacco in 106 kilograms of product weight between these years. The data is stored in a time series object called SIG. Analyse the components of the series. So that's the question. So let's have a look. SIG. So there's my series, SIG. It's a time series. Starts in 1965, finishes in 1989. Frequency is 1. Frequency is 1. All right. What do we do? What do we do? Well, I want to encourage you, go through the process, the steps. Okay, so let's head down to where's SIG? Okay, so let's do this. Here's the data. Okay, so it's annual, right? Let's make some basic choices. That's the first thing we want to do. Is this thing homoscedastic or not? Yes or no? Yes? Anyone for no? So again, take your fingers, run them along, right? Do they stay the same distance apart? It's a tough choice, isn't it? Right? This time series doesn't have wiggles. Why doesn't it have wiggles? It's measured once a year. Right? You don't have multiple tomes per year. So yeah, I reckon this is homoscedastic because if you just go from left to right, yes? Follow the fingers. Right? You notice they're not getting further apart. Some people think it's heteroscedastic because it starts by heading up and so you don't see an up and down to give you the two-finger reference, okay? But if you actually think about it, if it goes up, up, you can look at consecutive ups and work out if it's moving up by a different distance, and it doesn't seem to be. So I reckon this is homoscedastic. By the way, if you took logs, let's do it, and I'll show you what it looks like, or square root. So let's just change sig to square root of sig. Let's have a look what happens. That's the square root. What changed? Not much. Something changed. The scale. The scale on this axis changed, right? Has to, right? Square rooting things, numbers got to get lots smaller, okay? But the shape of the plot didn't change. Generally speaking, if you take transformations and the thing doesn't look any different, odds are it was homoscedastic, right? Odds are. So you can try that. So, first decision, is it heteroscedastic or homoscedastic? Again, do the fingers, do the fingers. All right, trend, what's this doing? Probably quadratic, okay? Probably quadratic. It goes up and then it comes down, okay? Now, I'm going to fit a quadratic to this, that's cool. But, you know, it's like the data's about cigarettes, so the data set should come with a warning, right? What's the warning? If you fit a quadratic, when you predict into the future, what's going to happen? Predictions are going to get lower and lower and lower because quadratic goes up, quadratic comes down. It ain't coming back. So, it's going to start going down and then it's going to keep going down, okay? Now, it turns out, of course, cigarette smoking, this is kind of what did happen. It did keep coming down for a little bit. And then there was a resurgence. I don't know why, because it's disgusting. But anyway, people smoke again. I don't get that. But so they didn't bottom out or anything. But remember, if you predict too far into the future, the only guarantee you have is that you're going to be more and more wrong. Okay? So a quadratic's probably good to fit in terms of the shape of the data. It's not going to be any good for long-term predictions, but that's where we're at. Okay? All right, so we're going to try and fit a quadratic trend. All right, so let's do that. I'm going to centre the series. You don't really have to centre it to fit a quadratic. You would have to fit a cubic. I think it's good practice to centre it just to make the numerical stuff work a little bit better. Okay, and again, the reason we centre time is for no other reason than when R has to take determinants of large matrices with big numbers in them, it struggles. Okay, and fitting a regression involves taking a determinant of a matrix, and if your matrix has very large numbers in it, you run into trouble. Why do we get large numbers? If you take numbers like 1985 and you take them to the third or fourth power, you get a very large number. And so determinants of matrices with columns with very large numbers cause trouble. So I'm going to centre time, it's just a good practice. Centering time does not change the model at all. At all. It just means that R can fit it. All right, so we centre time, we're going to fit a quadratic. What's going on here? Here we go. So we run this and we run this. So there's my model. Let's have a look at my model so far. Except I'm always typing in the wrong spot. Mod. Okay, there's my model so far. So, intercept is 27, okay. Coefficient of time is 0.23, coefficient of time squared is minus 0.032. All right, so that's the model that I fit. Oh, by the way, we never talk about the intercept, but we probably should. The intercept is the predicted cigarette sales in the year 0. Well, I'm not even sure they had cigarettes then. Right? The year 0 is apparently the year Jesus was born. That's how we do things. You know, it's a bit weird. Okay, so this would be the predicted cigarette sales when Jesus was born. But there were no cigarettes and they didn't even know about Australia. Right?
Sorry, just a question. So if you've got XT is the year minus 1976, then when it equals 0, should we...
Oh! Not the year Jesus was born. Thank you, Lauren. That was very, very well done. See, Lauren's corrected me, and quite right as well. We centred time. I forgot. Oh my God. Okay. So this will be the predicted sales when? It's 1976. Jesus was well and truly gone. Well, he came back. And then went again. Anyway, okay. Oh, well done. Good spot. Good spot. Okay. All right, let's have a look at the residual series. So let's do a plot of residuals model mod. Okay. Oh, sorry, I always forget to do it. So we want time of sig versus residuals of the model type equals B. Okay? So there's my residual series. Okay, now, here's what's interesting about this, right? Previously, we had a quadratic run through that dominated what you saw, right? Because it was so dramatic. Now we've fit that quadratic, and this is what's left. So this is my error series, okay? This is my error series. So what's the next thing we think about? So we've detrended it, put a quadratic through, we detrended it. What's the next thing we think about? Seasonal. What do you reckon we do? Nothing, right? Why do we do nothing? 2 reasons. Why do we do nothing? 2 reasons. Frequency's 1, right? And, better reason, there is no regular periodic behaviour, right? Why don't we fit a seasonal at all? We fit a seasonal so we can deal with the wiggles, right? No wiggles. Not even the blue wiggle, right? No, you guys are all too old, as it turns out. Usually I say jokes where you guys are too young. Now it's because you're all too old. You've not heard of the wiggles? Oh, dear. Okay. Well, it's only 1 second out of our day, isn't it? And cultural awareness is important. The wiggles. The wiggles. They've got new wiggles now. I don't like the new wiggles, got to say. See, they're the new wiggles, except for one. He's an old wiggle. He stuck around. Okay. Anyway, if you were younger, this would be driving you nuts now. You'd be cheering and, yeah. But the wiggles have sold out. See how they're selling milk? Anyway, all right. So sad, so sad. Okay. So we're not going to fit any wiggles, right? Because no one cares about the wiggles, evidently. And because there are none, right? Now, so, seasonal. Only fit a seasonal if you see regular, periodic behaviour. All right? If you don't see regular periodic behaviour, don't fit a seasonal. Yes?
So, what about the two?
Yeah? Oh, okay. So you're going, I think there's a regular thing here. It goes down, and then it goes up, and then it goes down again, then it goes up again, and I reckon it's going to come down again. Yeah. How much do you want to bet? How much money? How much money do you want to bet that's real? But you sound so confident. A cup of coffee? I don't even drink coffee. Would you bet $1,000? No way, right? Right, okay. So why did I ask you that? Well, the answer is, okay, because what you're having at the moment, and I hate to expose this in front of everybody, you're having a fantasy, right? You've got this fantasy that there's this regular thing going on based on really very little information, right? So I've got what, 20, 25 years worth of data here, and you're saying there's a big cycle runs through this, and it's going through its second bit. It's done the first one, and then it's starting the second one. That's a big call, right? Because you're relying on so much to happen over here, right? And you don't know, right? So it's a really good question, though. It's a really good question. And it gets to what your eyes see and what you want to see, right? And you get locked in to thinking around things a certain way. So a lot of people, when they're doing the assignment, they're going to go, okay, trend, yep, got that. Seasonal, got to fit a seasonal, got to fit a seasonal. Right, what do I see? And then you see stuff, right? Well, if it's there, that's fine. If it's not there, be really careful. Because if you see stuff that I don't see, I'll assume you're taking drugs. Right? And I might come to you and I'll say, what are you taking? It must be really good. Yeah. So I get it. And look, here's the thing. There might be big, long cycles in this. But you've got no right guessing that if you don't have enough data. All right? The one thing statisticians have to do is honour the data. And so the data here doesn't quite give you that. But it is a good question. It's a really good question. So save your seasonals for when you can see regular behaviour. Okay? All right. So the residuals I got so far are now detrended and deseasonalised because there was no season. Okay? So I can actually proceed and do a Box-Jenkins identification of these residuals. And you get this. Okay, so there's the ACF, right? Starts off at 1, goes in between the dotted lines and stays there. Okay? PACF, we're looking for things outside the dotted lines. They're on the line, in, right? They're all in. Okay? So again, we've got a choice to make. We either decide that this is white noise or we fit an AR1. Now I'm going to fit an AR1 again. I'll tell you why. Short series, right? We've only got 20 odd data points, right? Not very many. This is sort of right on the dotted lines. By the way, the reason I'm so cavalier about the dotted lines is that these are based on large sample theory. The idea that you might have 1,000 data points, right? They're based on large sample theory. So they're not nailed on, right? They could move around a little bit. So you can imagine this one's right up against the line, okay? I'm going to say that when I look at that previous plot, this one here, this doesn't look to me like independent data, right? It's got that mountain structure, okay? And so I'm going to say I don't think I can get away with white noise on that. I'm going to fit an AR1. Again, choices, all right? Okay, so let's fit the AR1. So let's go fit AR equals rake of residuals of mod. Because I'm going to fit an AR1, I use fit R first column. And I'll give fit R dollars coef first column. Okay, so my coefficient is 0.397. Okay, write down the model, look at the residuals. Okay, so this one probably is the most like the data you've got for the assignment, because the data you've got for the assignment's annual data, okay, and so the same sort of decisions will be made. But look, it doesn't matter what data I give you, go through the steps, okay? So we're just about out of time for today. By the way, what I'm going to do tomorrow is I'm going to go through at least 3 more examples, okay? But you're good to go, right? You can get started for sure on the assignment. So here's some guidelines. Please don't email me asking, is my model right? Because I shall simply respond with no. Okay? Because that's not what we're about. We're about fitting reasonable models. And by the way, don't ask me if your model's reasonable, because the answer to that won't be no, it will be I don't know. Right? Okay? And the second thing is, don't email me asking me to make the choices that you have to make. Okay? So don't ask me what transformations to use. Don't ask me, is there a seasonal? Don't ask me, is there a trend? Because the answer will always be, you decide. You decide. Okay? You decide. And again, this is not me being mean. It's just the whole point of the exercise is, here's data. You decide what to do with it. Right? That's the whole point. Okay? So anyway, see you tomorrow over the road, and we'll do some more examples. All right. I'll just log out of this and take the mic off. Stay right there for a minute. We're going to talk to Jinder about a similar thing. So you guys want to just stand there for a second and I'll deal with the